Good afternoon, everyone. It's very excited to present my paper here, and I'm a PhD student at National University of Singapore. My paper is about a classical principal agent problem with moral hazard, and the title is basically the first order approach to principal agent problems. So let's go straight to the model setting, because principal agent problem is what we adopted, and I think most people here, or almost everyone here, knows what the principal agent problem is. So in this model, a risk-neutral principal hires a risk-neutral agent with a limited liability contract, SX. We use SX to denote the contract is a non-negative function of the continuous variable X representing the outcome. And outcome X is influenced by the agent's effort A, which is unobservable to the principal. And distribution of X is denoted by capital F and twice differentiable in A, and the standard function is F differentiable in A. The agent's cost of functions BA, increasing convex and differentiable in A. The agent chooses an effort A that maximizes his expected utility under a given contract. An agent participates if and only if his optimal expected utility exceeds his reservation utility U0. So based on this information, the principal selects an optimal contract to maximize her expected utility. So this is classical setting of moral hazard principal agent problems. And we can, based on this model setting, we can formulate the principal agent problem use this program. We use OP, the original problem, the principal. So in this problem, the principal selects a contract S to incentivize the agent to choose an ideal effort, with AS here, subject to three constraints: IC, IR, LL, and their incentive compatibility, individual rationality, and limited liability respectively. So this program is actually the same as the Holmstrom-based model, Holmstrom moral hazard-based model in 1979. A little different is that this model assumes that the agent must be risk neutral, but in Holmstrom model, it assumes that agent should be strictly risk averse. So here's the difference. And this program looks very simple, but actually, and it's also widely adopted. And we have seen many applications use this model. But for this program itself, it's actually unsolved in general. This is because here are two challenges for this program. So one is that there are infinite dimensional decision space. The SX here is a non-negative function. We need to choose a general function, a function in a general space, right? So this is first difficulty. And the second one is the IC constraint. It's equivalent to an infinite set of constraints, because the argmax expression is essentially implementing inequalities given here. So to handle these challenges, the literature usually use the first order approach. That is, it induces a relaxed problem. In the relaxed problem, the IC constraint is replaced with a RIC constraint, relaxed version of IC constraint. The relaxed version here restricts the AS, that's the effort choice, to be a stationary point instead of being a global maximum. In the original problem, here is a global maximum because the agent should give a best response for a contract. But here, to simplify the programming for easy to solve, we just assume that AS is a certain point. If the agent's problem is concave or is unimodal, then RP actually is equivalent to OP, right? It's concave, so the certain point must be a global maximum. But this usually not the case because it is a necessary condition, not a sufficient condition. So this assumption, that is the FOA is valid. So it assumes that, literature assumes that any optimal contract to the relaxed problem is also an optimal contract to the original problem. This is because the original problem is very hard to solve. So this assumption is essentially endogenous and may not always work, right? So the literature provides exogenous conditions to justify this assumption. And we can see, we know that based on the model primitives, we can know when RP is equivalent to OP, then we can use our these insights to handle real settings. real scenarios. So exogenous conditions that justify FOA includes the Merlis-Rosen condition developed by Merlis and Rosen in 1980s, and also the Hughes conditions also given, and all conditions in the literature that justify the first order approach include Rosen's condition, Hughes condition, and all the following conditions. The two characteristics for this condition is that they are all established for a strictly risk-averse agent. Also, they justify the first order approach by ensuring that agent's expected utility is concave and thus unimodal. So this is a direction, very good direction, because we can prove, if under these conditions, we can prove that agent's expected utility is concave, then we can prove that RP equivalent to OP, right? But it raises questions if the first one is that we don't know whether these conditions can be applied in a risk neutral setting, because our model setting assumes that the agent should be strictly risk neutral. And the second question is that, is it adequate for practical applicability to focus on a unimodal agent utility function? That is why its goal for the literature is to prove that under the conditions, the agent's expected utility is concave. But why? I think in many real-world scenario or application work, the agent's expected utility is not necessarily to be concave. So we will discuss this part later. So let's continue. So with these questions, I read through almost all literature that solve this model, but I don't get an answer from them, and I also found that solutions in literature are not satisfying. So some assume that FOAV without justification. They just use first order approach and assume that it's valid, and then solve the problem. But we don't know whether RP is equivalent to OP. And some even worse misuse the Merlis-Rosen condition, which developed for a strictly risk-averse agent. They don't prove that the risk-averse setting can directly carry over to the risk-neutral setting. And some reformulate the model. So don't use the Holmstrom classical model, but use the same model setting with a different formulation. In their formulation, they can solve the model in some scenarios, but they are based on endogenous assumptions for contract. They assume that the contract must be, for example, must be monotonic, so they can so the contract's almost differentiable by Lebesgue's theorem, right? So they can use a new formulation to solve the problem. But this endogenous assumption does not guarantee that solve the contract is global optimal. And some use a simpler model. They solve the finite or discrete output levels and the Fanon effort levels. For example, Grossman and Hart, this very barbell paper, and they transfer the original problem to a convex optimization problem. So these scenarios, all of these methods cannot solve our original problem, right? Because they either use the reformulation with some endogenous assumptions, and or to simplify the model using the discrete, assume the discrete output levels. So given the situation here, we may think that the question itself, the risk neutral setting itself, is not very interesting or is not important. But actually, this is not the case, because the risk neutrality and limited liability model is widely adopted, including many influential papers presented here. So given the situation here, we expect that we can find a rigorous solution approach that solves the original problem without sacrificing optimality. And we hope that for practical applicability, the solution approach to be clean and crisp and can accommodate widespread instances. And we hope the optimal contract can be a simple contract that can be easily used in practice. So to answer our questions and to give our solution approach, we start by providing a counterexample to show that the answer to the first question is actually no. That is, the Merlis-Rosen condition does not imply the first order approach valid under a risk neutral setting. Now here is the Merlis-Rosen condition. So it's widely used and it's the most celebrated condition that justify FOA. The first one is MLRP. It's very general and almost held in all distributions. But the second condition is convexity condition. Is not very general. We will discuss this later. And this is our counterexample. We show that by providing a non-monotone contract as C here, we show that this contract is optimal to the relaxed problem for this example, but it's not the optimal contract to the original problem. And this counterexample is also a common distribution, beta product distribution. So we show that a Maurice-Rosen condition actually cannot transfer to the risk-neutral setting. This answers our first question. So an intuitive thought is that we might find stricter conditions for the first order approach for a risk-neutral setting because the Maurice-Rosen condition cannot hold. So and the first order approach is very easy to use. So why not find the stricter conditions? But the Maurice-Rosen condition, especially for the second term in the last slides, is criticized to be too restrictive, and it includes many common distributions. So stricter conditions can be maybe little use in practice because if it is stricter than the Maurice-Rosen condition, and Maurice-Rosen condition is criticized for being too restrictive, so the new conditions may be even more stricter and maybe little use in practice. So it suggests that for FOAB may be too demanding for the risk-neutral setting. So how to solve the original problem? And we provide a new perspective that motivated by a discovery of an important structural property of relaxed problem, optimal contract. And before we describe our perspective, we give a definition here. We find this simple contract is called quarter-bonus contract, and it's actually a one jump step function. So if the outcome exists a quota, then the agent will receive a bonus B, the constant. And this contract is also, I think, is very popular in the marketing sector. And we find that it is sufficient to focus on the quarter-bonus contract for the relaxed problem in general. And the proposition 2 says under MLRP, in the relaxed problem, for any feasible contract, we can find a quarter-bonus contract that induces the same outcome for both the principal and the agent. So that means we can just focus on the quarter-bonus contract because other contracts can be matched back. Any feasible contract can be matched by quarter-bonus contract. It reduces the dimension of the relaxed problem. So relaxed problem can be easily solved by restricting our attention to the quarter-bonus contract. And in addition, this property does not extend to linear contracts or dead contracts. So for well-known simple contract, I think the quarter-bonus contract is the unique one that has this property. Based on this discovery, we propose a twist to the first order approach. We not focus on, we propose the FOAB QB. It's a new notion here. And we define FOAB by the first order approach is valid for the quarter-bonus contract. If any quarter-bonus contract that is optimal to the relaxed problem is also optimal to the original problem. So FOAB QB here is also indulgence, but less restrictive than FOAB. We know that FOAB says that any optimal contract to RP is also optimal to OP. But here we don't care about the non-QB contract. We focus on attention to the quarter-bonus contract. So it's very intuitive that under MLRP and FOAB QB, if the optimal contract to RP exists, then there exists a QB contract that optimally solves OP. But the question is, when does FOAB QB hold? And if we don't know when FOAB QB hold, that if you give me some like model parameters, we don't know if the FOAB QB here is applicable. So we need to address this problem. So before we give our exogenous conditions, we introduce a property for feasible contracts in OP and give a lemma here. So the Cartier characterize a feasible region for agent effort A and agent expected utility C. So for any agent efforts A and expected utility C, for any AC pair induced by a feasible contract for OP, it must belongs to Cartier. So Cartier is a feasible region. And now we give our exogenous conditions and the condition 1 and condition 1 prime. We require MLRP. MLRP is very general, but for the second term, it is maybe not be very easy to verify. So we will prove that these conditions are very general and can hold in many scenarios. And we prove a relationship among our conditions. The Morris-Rosen condition implies condition 1 prime, and condition 1 prime implies condition 1, and condition 1 implies FOAB-QB. So FOAB is endogenous. FOAB is also endogenous, but we don't know when FOAB will be hold. So we can fully solve the original problem on our conditions. And this we reduce that an infinite dimensional problem with infinite many constraints to a 2-dimensional problem with 3 constraints. It's very intuitive that if we can restrict our condition to polar bonds contract, and then we can reduce dimension. So we also show that even the optimal does not exist, we can still solve the problem and provide a epsilon optimal contract that is close to the supreme, because it's also because we can focus on the polar bonds contract. And we show that if the optimal contract exists, then we could then the agent expected utility must be the reservation utility. The IR constraint must be binding. So now we show some examples to show that our conditions are actually very general. We define the class 1 distributions, and for class 1 distributions, for example, the exponential gamma all in the class 1, and class 2 distributions, beta prime F distribution are in this format. So for these 2 distributions, we show that if Cassie, in this model setting, if Cassie follows class 1 distributions, both our condition holds, the Morris-Rosen condition hold with the following constraints. And in most of the case, this is not an expected utility. Agent expected utility is not a unit model because most distributions class 1 have eta positive. And the proposition 6 says the same thing for the class 2 distributions. So condition 1 and condition 1 prime are far more general than the Morris-Rosen conditions, and focusing on unimodal agent utility function is not adequate. These answers are 2 questions. So now here's the examples for solving OP explicitly. And we can reduce the problem in a simple program and very easy to solve. And even if it does not exist, then you can focus on the simple program and easily give 99% supreme. So in this paper, we show that the Morris-Rosen condition cannot justify for the risk neutral agents. We show that focusing on unimodal agent utility function is not adequate for practical availability. And we propose that our new solution approach. We show that focusing on QB contract is sufficient for the relaxed problem. The notion of FOE QB is much better than FOE for risk neutral agents. And condition 1 prime justify FOE QB and can be implied by the MR condition. They are general enough to accommodate numerous common instances, include cases where agents expected utility is non-unimodal effort. We show that focusing on QB contract is sufficient for the original problem under our conditions. So here's the conclusion in this paper, and thank you.